Welcome everybody to the last session of the morning. It's on soft matter, which is a field combining physics, biology, and chemistry. And we have two speakers. The first speaker is Professor Oleg Gang. He did his PhD at the Bar-Ilan University, then postdoc at Harvard, and he's now a professor at Columbia and also a group leader in Brookhaven National Laboratory. He will tell us about part of his work on the integration of DNA with inorganic and biological nanocomponents into well-defined objects, about organized nanoparticles and proteins, into ordered 3D arrays, and a few more things. And since he has 50 slides, I will have to remind him at some point, and we should not waste any more time. Please, Oleg.
Thank you. It's my honor to be here, and I would like to thank you organizers for inviting me to this exciting event. I will be happy to share what is published and what is not published, because that's the most exciting. And it's clear from my talk where I will tell you about how we are thinking about creating kind of well-defined nanoscale systems, both static and dynamic. So all this motivation comes really from the point of view that we limited to this periodic table, and it has not been really a limitation. But as soon as in the last couple of decades we have development of different type of nanoparticles into different type of objects, and this allows us access different properties, we essentially departing from the universality of chemical bonds, because now every particle somehow is different, it have different ligands and so on. And so from this point of view, what we're losing this kind of generality of chemical bonds when we're dealing with nanoparticles. Every system is kind of unique, which is good, but essentially it's bad because there is no platform. So one potentially can use particle shapes, basically to build on particle shapes to assemble them structures. It's possible to use interactions provided by ligands, but all this becomes extremely system specific. So when we started to think about this probably about 12 years ago, we wanted to develop an approach which will be kind of general enough that anything can be organized kind of in well-defined systems. Anything, I mean, nanoscale objects. So essentially, that's kind of the challenge which we outline, how we create well-defined bonds for those types of objects like nanoparticles. So from this point of view, it's kind of very clear that we want to some degree to decouple the properties of the particle, which is essentially often driven by their kind of inorganic core, from ways how they can connect and assemble into larger scale systems. And so if one can now reinvent how particles will be assembled and essentially what type of bonds, you don't need to be limited what is provided by nature and periodic table. And this is kind of what's from the beginning or kind of evolved as a wish list, what we'd like to have. And as a comparison, this is atomic type of system. So directionality, as clear, is important because it's allowed to diversify the structure, and this is typically it's given in atomic system surveillance. However, there is a new type of bonds properties I would like to introduce as colors, and I will explain more what they mean. By colors, I mean addressabilities. It also both implies orthogonality of interactions as well as very specific type of interactions, and that's kind of, I will use the word color to emphasize this. The second aspect, as I said, aspect is modularity, and this is something unique that doesn't exist really for atomic systems. Another aspect of modularity, essentially to build more complicated systems, you cannot rely only on one type of components. It's obviously this is the way how molecules are made. The another one is that from some self-assembly point of view, it's quite important to have reversibility of interactions, and that's essentially to some degree can exist in atomic system, but it's something which we would like to have not only reversibility, but ability to switch them on and off and activate in demand. And the last one is length tunability, because particles provide us with functions. In many cases, functions are determined by their distances. Having this type of kind of in mind, one of the platforms which we saw would be suitable to implementing something like this is based on DNA. So the topic of connecting particles to DNA is not really new, and it was not new 12 years ago, because somewhere in mid-90s, both Paul Olivasades and Chad Mirkin demonstrated that essentially you can take inorganic particles, glue one or many DNAs to the particles, and in this way, in principle, you can induce aggregation between the particles. However, just relying on this hybridization is not sufficient to form three-dimensional lattices or two-dimensional well-defined systems and so on. So part of my talk, I will discuss really what is important. And so when we started doing this work, essentially, yes, you can create particles of graphed to particles DNA. However, typically you would observe some kind of non-specific aggregation. And so the reason was that it's not only driven by pairwise interactions between two DNA from two different particles, but there are more complicated and, due to this kind of shell structure determined by the composition of the shell, the property, rigidity of DNA, and so on. And so kind of from the interaction point of view, it's not really pairwise anymore. There are different collective effects, even many body effects when more than one particles come to interact. And so when we started to think a bit more rationally, what is really required to crystallize particles using DNA as a kind of driving force for self-assembly, we started to think that really it's necessary to have equilibrium potential which allows for crystallization. From other point of view, it's necessary to establish a proper pathway. So from the point of view of equilibrium potential, one can imagine this potential not necessarily very suitable, because it's kind of very difficult to crystallize when you have such strong interaction, essentially no repulsion. This potential might be too soft, and it's kind of, there is no much difference between metastable disorder and stable order phase, and this might be kind of more appropriate. And so there are different ways how we explore how one can tune interaction potential, still preserve addressability and complementarity to take advantage of this kind of hybridization between the particles. And so one of the ways which was successful is simply to use a spacer as a way to tune this repulsive interactions, where attractive can be tuned through the hybridization. And so the second aspect is really the crystallization pathway. It's not sufficient just to mix them. It's necessary to find the conditions, because, and this is where reversibility of interactions come into the place. And so it was important to realize that we need to have in situ tool how we can trace and monitor the system transformation and kind of how it goes to the crystallization. From this point of view, we have been relying heavily on X-ray scattering, which can be done in solution, and by analyzing two-dimensional pattern, we can extract information about structure. By doing all this and optimizing this kind of interaction potential as well as a pathway, we were, for the first time, we were able to demonstrate three-dimensional crystallization of nanoparticles driven by DNA. I just want to mention this, like 10 nanometer gold particles, 50, 60 DNA per particle. And that's kind of give you ability to create these crystals. The crystals is body center cubic crystal, and it's kind of the simplest, essentially, structure which satisfies the conditions. Blue doesn't like blue because they have the same DNA, but red doesn't like red, but blue and red have complementarity, and that's kind of the system which satisfies this condition. It's conformed by small angle scattering. The same type of approach can be generalized to different types of particles, not only gold, and so later we use catalytic as palladium, magnetic as iron oxide, fluorescence, different type of quantum dots, plasmonic, both silver and gold, essentially to graft, to start from the particle which might have initially very different type of ligands on them, and then graft DNA by different methods, which I'm not going to discuss now. And that allows us essentially to have different functionality provided by the inorganic core, but have the same type of approach which allows to build systems. And so you don't need to be limited to a system which contain only one type of particle. Essentially, we can mix and match. And so different types of particles can be brought together in this kind of binary mixtures. So from this point of view, for example, this is kind of more material side of this diagram, and this is more like a physical parameter space. And so let me tell you a little bit. From this side, we can, for example, take iron oxide particles and connect it with quantum dots, and so you will have system which might be optically active, but also can be responsive to the magnetic field. Even so, I'm not going to discuss now all properties which we investigated for the system due to the length of the talk, but I wanted to stress there are many interesting opportunities to have this kind of multifunctionality through mixing particles. So in principle, in all those cases, we essentially can change the interparticle distances from about 10 nanometers to somewhere sub-100 nanometer regime by simply changing the design of the DNA motif. From understanding when the crystallization occurs and where other phases happens, essentially we found out that for particle of similar sizes, the main parameter is number of DNA per particle, and essentially in the regime of a larger number, 40 and so on, we obtain crystals. Then for smaller number, it will be weakly ordered, and for below 20, it will be essentially formation of the clusters. And just it tells you that from percolation point of view, 20 is a very big number. So why it's 20 is it just tells you indications that probably there is certain bundling of DNA between particles. So this kind of approach, I just wanted to demonstrate it applicable to different type of materials, and even such a relatively simple type of organization like BCC lattice and some other simple lattices can be explored from other point of view, how we can take advantage of DNA plasticity in terms of building reconfigurable systems. So I will spend a couple of slides discussing transformation in this type of system. So the very simple type of transformation is basically induce lattice change. Of course, one can use different conventional parameters like temperature, pH, and so on. But here I really wanted to focus, and we have done this type of stuff, but I really here wanted to focus on highly specific triggering, so which is promoted by DNA. So for example, the particles are connected by this bridge, which is single-stranded DNA, and which essentially designed in a way that by having one DNA strand, it can be in this type of configuration. There is a loop which is stabilized, and we can remove this through the replacement reaction, go back, and be in this configuration. The difference between this configuration approximately 6.5 nanometer, which is approximately 25% of the lattice distance. So essentially, we can start from the crystal, and by adding different types of DNA strands, we can switch the lattice constant in this type of organization. Changing the distances, it's interesting, but it's not so exciting. It's much more exciting to think in a way how we can reprogram bonds on the fly, and we can change global state of the crystal, for example, to go from one symmetry to completely different type of symmetry. And again, it's not induced by any physical parameters, conventional parameters, but rather specific DNA strands. The way how it can work, for example, if we created a system which is now the same type of BCC lattice which I told you before, essentially, this type of crystal essentially balanced between repulsion and attraction, which I discussed. However, if after the system is already formed, the crystal is already stabilized, and I can change on the fly the shell, they need to find a new equilibrium state, and as a result, this kind of balance between attraction and repulsion is shifted, and new type of crystalline organization can occur. So to realize this kind of idea, essentially, we start from these two types of particles. However, I want to point your attention that we're not using all ports. Some of the ports here on the particles are unused. That means that we form our kind of what we call mother state, mother phase. However, those ports can be engaged later when we're adding DNA strands which will specifically recognize those ports. However, those DNA strands which will be added can essentially carry different type of function. For example, this is what we call just stapling. Those stapling functions essentially will connect X to Y or X to X, no matter what types of particles there. So essentially, it will shift significantly to the attraction point. On the other side, we can add what we call blending. So now the DNA which is supposed to go to X can go to Y as vice versa. And as a result, you're also kind of changing the balance between repulsion and attractions. Finally, you can introduce DNA which will be purely introducing repulsion. It's not going to connect to anywhere. So by simply kind of doing something of this kind, we're adding DNA, and this allows us to observe the phase transition from one crystal, for example, to another. We can monitor this in situ using small angle scattering, but we start here from this pattern which corresponds to BCC. We're adding DNA strands, and we just do nothing else, just waiting and monitoring. And over the approximately 12 hours, you see the transition from one state to another. We can analyze if there is no intermediate state, BCC is dying, and FCC is appearing here. And there are all other type of characterization which can be done, essentially looking at the change in the correlation length during transitions and so on. But this type of kind of philosophy can be applied where we can add all those different types of DNAs and which trigger different type of transitions. So essentially, you start from this mother phase, and depending what type of DNA you will give, you transition system to two different pathways, and so different pathways will lead to transformation to the four different type of organization. So that's something which is quite exciting, because in some sense DNA is kind of biological compound, maybe not completely, but at least in this case, it's a very short primer DNA, and we can induce the reorganization of nanoparticles. And again, as you imagine, one can have plasmonic or light-emitting particles, so you can have certain kind of properties associated with three-dimensional crystals, and having DNA potentially change these properties can be exciting. So from this point of view, it's kind of can look at this as a genetically modifiable materials, because we're able to transform materials by adding simple DNA strands. However, let's come back to the kind of the main topic that I really wanted to discuss. It's a question how to promote the organization of well-defined system. And so it's not just a question of well-defined, it's a question of the system which we potentially can design. And this kind of notion of inverse designs, that we know from the beginning what we want to build, and we're able to build it from nanoparticles, that's kind of one of the most important ideas that we're trying to explore. So it's not a question that we only want to understand why self-assembly happens and why this phase appear, but we want to be very prescribing in a way what type of structure will be forming. And through other remaining time of my talk, I will be basically focusing on this aspect. So you very quickly realize that as beautiful DNA as is, it's very limited, because from nanoparticle point of view, DNA, it's a contact interactions, provide interactions between basically the first, between particle in the first coordination sphere, maybe a little bit in the second. So from kind of any physical point of view, to induce complicated structures, it's necessary to have much more longer-term range of interactions if you're talking about isotropic interactions. And so this is my one slide overview of everything I know about kind of colloidal assembly from the point of view what ways people develop and what is available there if one would like to diversify this type of ability to build structure. So first of all, of course, if we're talking about just spherical isotropic particles, mixing particles of different kinds, different sizes allows to access not many, but certain kind of types of structures. This can be further diversified if we're taking into account the ligands which can provide interactions. However, it's still kind of limited, and the most importantly, it's very system specific. If you want to take this particular particle and make this lattice or that lattice, it would be impossible. You have to do everything from the beginning. Having in mind that particle is our kind of functional building blocks, you would like to have approaches which wouldn't be limited by something like this. The second approach, which has been mainly explored theoretically, and more in the last maybe 5 years, we can see many realization, a number of realization experimentally. It's approach with patchy particles. Essentially, to some degree, it mimics the valency of atoms when we have particles with prescribed kind of patches which provide directional interaction. So this has been realized for micron-sized particles. It's quite challenging, and I'm not sure to what degree it will be feasible. Probably it will be, but not for now. To realize for nanoscale particles, particularly demanding that billions of particles will be exactly the same. So, but however, this approach does allow you to departure from the isotropic interactions and take advantage of this kind of anisotropic interactions to create more complicated structures. The approach which we kind of proposed and developed is kind of still to not to use isotropic, but to use anisotropic interactions, but at the same time to simplify. That means that we're not touching particles. We want to introduce blocks here, which essentially provide coordination for the particles through, for example, their geometry. So this way, we're kind of outsourcing the problem, and we're not our particle preserved kind of intact. So there are different kind of implementation of this, and I will share with you two of those major, and essentially you can see them. One of them is a facet-driven, and another is vertex-driven. So I will start from the facet-driven approach. In the facet-driven approach, essentially you have a particle, and let's introduce this kind of abstract block which provides certain degree of coordination. So this abstract block is shown here as a fourfold, just kind of for simplicity, two-dimensional. And essentially the idea is the role of the DNA here, that if you're going to mix two particles of different shapes, you obviously will get phase separation most of the time due to the entropic reasons. This is here where the DNA comes in place. So DNA prescribes us that this block, it will be complementary to the particle. So if you look at this kind of from the local environment, this block essentially allows to coordinate particles according to the symmetry of the block. The hypothesis underlying here is that this can propagate, and the crystal structure can form, and the crystal structure, the symmetry of the crystal structure will be related to the geometry of this block. Of course, it's not given that the structure will be crystalline. It may be also a disorder, and that's something which we started to investigate at that time, trying to understand that what parameter control really crystallization. If you look at these particles kind of in a close proximity, you will see, so we used cubes for example, as a way to coordinate spheres. And if you look at the cubes here, you will see the DNAs which connect those two particles. The DNA which here in the center can be to some degree compressed. Here the DNA can be extended, and this is because we have quite different curvature of those two objects. So this means that you need to find the certain kind of parameter space for the DNA to exist to satisfy those conditions. This is what we have done here. We looked at the rigidity of DNA as well as its length, and it's found in a certain regime where it's flexible but not too flexible, and it's not rigid already. And so we can change rigidity simply by going from simple single-stranded to double-stranded, because the persistence length changes by factor 50. We can find this regime where the crystallization can occur. But another aspect is also the relative size, because if spheres in cube are comparable, sitting kind of in the middle of the cube allows to satisfy all the bonds, and shifting to the side essentially is not so favorable because you're losing some of the bonds. If the particle is too small, in this case, it's caused basically almost the same to sit anywhere. So from this point of view, if you have particles of comparable sizes, you will have this kind of self-alignment process. If you have particles which are significantly smaller, for example, it's essentially caused the same for particle to be here, and it's very difficult to achieve crystallization. So having kind of this exploration in mind, so indeed we could observe this kind of co-crystallization of two non-complementary shapes, and from the point of view, you can also say that cubes essentially dictate how spheres will be organized. In this case, they're in six-fold symmetry, which is completely not native for them. It's a sodium chloride type of system, type of structure, where you have C alternating order between cubes and spheres. And we can also, we always rely on scattering for the really quantitative analysis, and that's also confirmed by scattering and modeling. So we have done something like this not only for cubes, but also using octahedra block, also comparable sizes around 40 nanometers from gold. And we can also obtain kind of crystallization driven by octahedra. However, if you want to kind of generalize this type of approach, you very quickly realize you're limited what type of shapes you can get from nanoparticles. So from this point of view, it's good to go back to the molecules. And so this is an approach which has been proposed by Paul Rodeman in 2006, and DNA origami. For those who didn't hear about this, the idea is that if you take a very long DNA strand, in this case it's M13 close to 8,000 bases, essentially this strand is not just a polymer, but it has a very particular sequence by providing, for example, staples which connect fragments which might be very far from each other from linear point of view but have a right kind of addressability to recognize by the staples, you can kind of bring those fragments together. You can give too many 150 strands, for example, and it allows to fold it. So Paul first demonstrated this approach for two-dimensional system, but this approach also can be generalized now to 3 dimensions. So this allows to build kind of structures out of DNA of desired shapes. Now, imagine that now we have a kind of this idea in mind that we can build 3-dimensional, quite complicated linkers, and this linker has very particular geometry which we can predefine. So this is what we are doing here. This is octahedra. It has dimension approximately 30 nanometer side. And so those 1, 2, 3, 4, 5, 6, those are vertices which can be prescribed to have a different addressability through the incorporation of single-stranded DNA. Now, from the point of, first of all, we can confirm that we can, using cryo-TM, that we can create this type of object. And the second, we can use those vertices essentially as underlying scaffold to position particles in 3D. And this kind of like a supermolecules, but again, made out of particles, fully coordinated by this octahedra. Because we have a full control and addressability, those 6 addresses can be the same. In this case, we're having this type of situation, but they also can be different. For example, in this case, we will have 3 particles of different sizes, which have different DNA, will have different complementarity. As a result, having the same underlying object, but repositioning or recoloring the bonds, we essentially can build non-chiral and chiral type of organization from those 3 types of particles. In non-chiral, the particles of the same size will be kind of on opposite vertices, and in chiral will be on the same side. And so because particles are plasmonic, we also can check that using circular decoratism, even though the coupling is very weak because the distance is relatively large, but it's still something which we can see that it's possible to observe. So now having this type of idea for building particles in a finite size 3-dimensional kind of clusters, one can explore this, why not to use this as a way to cross-link particles in 3D. And that's kind of approach which we have been exploring here. You can generalize the particles now using this type of DNA frames, and that allows us essentially to position particles in this kind of DNA nanoparticle framework. Now, again, the underlying hypothesis here is that the lattice symmetry will be determined by the design of the frame. And so from this point of view, by having the same type of particles and providing different type of frames, we in principle can induce different type of systems. So due to the lack of time, I'm just going to jump a little bit quicker, and basically to show you that indeed this can be realized in different type of lattices from the spherical particles by having all these kind of frames can be provided, as we can confirm by X-ray scattering. So now, having this in mind, we wanted to address also the question which have been kind of outstanding for 25 years or so in the field of self-assembly. It's the formation of diamond lattice. So the diamond lattice was first proposed in late 80s because of the photonic band gap materials interest for assembly colloids, but then somehow it became kind of one of those structures which seems to be easy, but in principle was very difficult to make for the reason, one of the reasons it's open structure, 34% by volume, and there is very easily to destroy the lattice through the rotations. There are several phases which have similar kind of energy. And so from this point of view, the approach we have been kind of trying to explore, it's a question how we can, using, for example, tetrahedral motif to create a 3-dimensional organization of particles in a diamond type of lattice. So what I wanted to stress here, this is our tetrahedra made out of DNA, and now we essentially imagine that it can be attached to the particle direct through hybridization. There is no particular red triangle. It's essentially just hybridization zone. There is no particular prescription on the particle. It's a completely isotropic particle. However, this kind of triangular footprint allows us really to look from the point of view what's the size of the footprint in comparison to the particle. And so if you look from the point of view and asking what the best arrangement of triangles on a sphere, you can come up with a different type of arrangement depending on the relative size. It turns out that in certain kind of regime, particle size to the footprint, this type of organization would be kind of the most beneficial, the best, and this at the same time, since it's a footprint, it's kind of from 2 dimensions, the positioning of the triangles allows us to orient the tetrahedral in 3-dimensional space. Now, if you take this kind of picture and project how it will look in 3D, that will look like that. And so from this point of view, what you just basically you form FCC lattice, which is very simple lattice. Why to go to such complexity to build such a complex lattice? And the point that this is empty tetrahedral, we can populate this tetrahedral with a particle inside, and that allows us essentially to build the diamond lattice from the point of view of particles. So we can verify this using scattering, and we can confirm both FCC when there is no particle inside, and when we add particle inside, we create diamond, as well as we can also image using electron microscopy, and this is atomic system, FCC and diamond, and this is a system which we build, which is approximately 100 times larger. So this type of approach also allows us to build lattices, and often people ask this question, these lattices are made out of DNA and particles, they're not necessarily useful as materials, and so having this in mind, we developed the approach essentially which allows us to create 3-dimensional replica of those type of structures. We can deliberately silicate DNA only. This allows us to create essentially this 3-dimensional architecture which fully replicate what we made out of DNA. And as you can see by scattering, it's basically almost the same. There is this about 10% difference in the lattice constant. So what is important is sustainable above 1,000 degrees, above 8 gigapascal, and because we have access to the different geometries of the frames, we essentially can create different type of architectures. We're very interested to explore mechanical properties and relationship between the architecture and mechanical properties. So another aspect that I wanted to share is a question that how you build structure which is non-periodic. The structure which is non-periodic, in principle, one can imagine that it requires many different kind of addresses to encode different types of components. However, if we look from the point of view of biological, the human genome is on the order of less than 2 gigabytes, and your favorite operational system is significantly bigger. And so the question is that maybe we don't need to prescribe the position of every object, but we rather need to prescribe to some degree the instruction, how it's supposed to assemble. So this kind of motivation was what started when we started to think about how we can build this kind of structures which non-periodic, and how we don't want, when we don't want to provide all information to the system about every point. And so one of the implementation, relatively simple, what we came up with is the so-called polychromatic particles. Those particles essentially have a color bond, but they also have directional bond. Now imagine that we can build the alphabet out of these particles, and essentially those particles able to connect in topologically different ways. So this is like T, this is like L junction, this is Y, and so on. So the specific design of this is shown here. We have DNA origami where particle sits inside, and there are a number of DNA strands. It's not one, it's 8 of them, which are different, allows us kind of to encode this color. So the color is not provided again by one DNA, but rather by 8. So now when you build different type of structures, essentially you're mixing different type of this type of letters, and you create different type of words. You can get both periodic, non-periodic structures, clusters, 2-dimensional and 1-dimensional array, because everything done here now in planar. So having this kind of in mind, so we were able to create, by mixing different type of components, polymeric-like structure, either linear or zigzag, also clusters and 2-dimensional. So I wanted to stress here, this is what you see here, it's histograms, and so what you see here essentially, obtained from AFM, is that we can quantitatively understand the formation of those structures by taking into account the hybridization energy and the stoichiometry of the mixing of the bonds. So in something much more complicated, like Leonardo da Vinci Vitruvian Man, a kind of implementation at nanoscale can be done. Again, this is a low resolution, but in this case, we're able to use these 14 components and essentially mix in the stoichiometry ratio, which corresponds to this kind of low-resolution design that lead us to the formation of this type of architecture simply by mixing those components with prescribed structure. So I want to stress the yield is very low, 5–6%, but again, it's significantly higher than yield of producing human. So, I know that I'm kind of close to the end. So going back to this challenge of how we're taking this kind of nanoscale object and big crystal and how we can assemble in a different type of architecture. And so I wanted to share with you this unpublished results. We're essentially asking this question. We can think about DNA origami to some degree as a building block. So unlike, we don't need to think about this building block only as a polyhedral shape. We rather take advantage of the valency which can be provided by the vertices. As a result, if we want to create the crystalline organization, it's not driven anymore by the packing consideration, but it's strictly driven by valency. And so this is example how we can build, for example, empty lattice. There is no objects here out of DNA origami. So we have been able to realize this, and as you see, by small angle scattering. But what it gives you essentially ability to create an empty bookshelf, which you can populate with a type of object you would like. So the underlying framework is already kind of decoupled from the property of the object. Now you can use different types of objects, and I will show you a couple of examples, from particles to enzymes to proteins, where you can essentially to build three-dimensional organizations. So it doesn't have to be limited to octahedra. We can build from cubes. We can build, for example, again, from tetrahedra and build now also diamond of different kinds here. But it also gives us a power to revisit this question, which Ned Seaman, who is a founder of DNA nanotechnology, proposed in 1982. It's a question how you organize protein in three-dimensional arrays. This question had not been resolved till now, even so the DNA nanotechnology field now is relatively mature. And so now, having this type of in mind, we have been, for example, using very simple streptavidin as a way to create this kind of object which coordinate streptavidin because it has four-fold symmetry within octahedra, taking advantage for symmetry of the vertices, and allows us to create this object. This object is cryo-TM reconstruction. This unit block essentially now can be formed into crystalline organization, and that allows us to form crystals which are not crystallized by conventional crystallography, but rather organized. So, of course, this is not crystal which is going to be molecularly defined, but it's not. We don't have to look only from the protein crystallography. It gives you ability to create three-dimensional arrays for a variety of potential applications. So from this point of view, what I wanted to stress now, we have ability to create this kind of modular design where DNA essentially can be can provide us the framework to position particles inside. As well, we can take advantage of the these color bonds, polychromatic bonds, from outside to build different type of structures. So kind of philosophically speaking, we can imagine not only controlling who interact with who, but also controlling the whole pathway of assembly. And this is something which is probably we didn't even think before. Just to show you that the same types of blocks through this kind of color interaction can allow us, for example, to create kind of very different type of lattice, which is shown here. 4 types of octahedra now can allows us to, for example, to build this tetragonal unit cell. And as you can see here, this is kind of three-dimensional organization silicated. The same type of approach can be applied to the enzymes, and this is a very recent unpublished work where essentially we can explore collective effects of enzymes and their colocalization in three-dimensional space. This opens interesting opportunities for enabling certain kind of molecular circuits in 3D and so on. So the way how I see the future is we kind of now able to create all these different building blocks, almost irrespectively of the nature of the components, able to organize them. And we have certain advances. It's very far from completion, but at least we know how we potentially can do. What I see as a future, and this is what I wanted to really to bring here as a grand challenge, is now we can think not about materials, just something static or something which can be just is changed by stimuli, but we can, in principle, thinking about animated material system where you have all those components, but you also have controllers, which allows us on the fly to take advantage of ability to reconfigure those systems, and those can be even in certain kind of feedback. So we're working on, for example, implementing different components of the controllers, amplifiers, receptors, and so on, really to establish. This is not necessarily mimicking biology, but to some degree expanding in a way how this marriage between the materials and devices can occur. And so that's kind of what I wanted to, so this kind of implementation of some of the amplification which we're able to achieve. Within this, I would like to finish. I would like to acknowledge people in my group over the years and my collaborators over the years, and thank you so much for your attention.
Yes, in view of the times, we'll take very few questions. Itzhak, you want to be here?
Thank you. A question, it's a general question. How do you, because this DNA, complementary interactions are rather strong, how do you avoid falling into kinetic traps? Like a general strata problem.
So I think it's a balance between a degree of addressability you want to have, and so because you essentially can change the number of base pairs will be engaged, as well as you can change the melting temperature. You can tune a system to the so those two main parameters essentially allows you to change this.
And it's always achievable.
I'm sorry?
In your experience, this can always be done, right?
No, it's not always.
Not always.
You need to be within certain range. Yeah.
More questions? Thank you very much.
Thank you.
Very interesting.